Hello, my name is Raul Martin Rebana. I'm from Cybernetica, and I'm here to talk to you what's new in ZK secrecy. So ZK secrecy is a domain specific language, and the first slide is always to justify our existence, right? So why did we make a new DSL? And we entered into a DARPA project called CIV with our friends from Ligero and Galois. And in that project, we wanted to make zero-knowledge proofs, which are in environments where zero-knowledge proofs currently are not. So we wanted to aim for big circuit sizes and more complex problems. And so what we wanted to capture with our language was that in a zero-knowledge proof, you have these two dimensions for information. One is the domain. So for example, it's not just that the value could be public or private. It's that a value could be private only for the prover. It could be private such that only the prover and the verifier can see it. Or it could be fully public, in which it is known during compile time. Another quirk of zero knowledge is that we have on-circuit and off-circuit computation. So anything that is actually executed within the proof versus stuff that the prover could do like in their head. And we took these notions and we built the type system from them. So for each variable, like on the right you see x is int pre-prover, we have this kind of triple where one is the unqualified type, and then we have what stage it is and what domain it is. So for example, x pre-prover is x being int pre-prover means that it is off circuit and visible to the prover only. The slide switcher is currently not operating. I think the cursor may have been moved. Thank you. You can also classify, so there's like a ordering between these values. So for example, something that is in the public domain can be brought to the prover domain, but it cannot go in the other direction. And similarly, anything that is on the protocol, so like that is on circuit, can be also brought off circuit. So like obviously if you know the value, so you take it off circuit and then you do some computation with it, and then you can do some witness expansion with it, where we allow new wires to be created with this wire operator, which allows you to move from pre to post. And then obviously, as it is a new input to the circuit, typically it involves some checks as well. So this differs a bit from the other languages, which typically have like a public-private type, but those tend to conflate two things, either to conflate the prover and the verifier, in which case certain checks cannot be automated exactly. For example, if I have some process in which I'm loading in integers, and I wouldn't trust the prover to correctly hand them into me, so I might run some checks when the prover applies these integers, but not when the verifier does. This cannot be done if we do not differentiate between prover and verifier. Similarly, verifier and public can be conflated, in which case for example, with like public, we can know what is known during compile time, and then we can do some certain optimizations, which we can't if we just assume that it's a verifier input. And well, this type system might seem complex at first glance, but to be frank, so is zero-knowledge programming. We have taken the approach that, given the difficulties in zero-knowledge programming, we shouldn't have to shy away from some of the intricacies that zero knowledge brings us, because any programmer writing a zero knowledge program already needs to keep track of in their mind, for example, any constraints, because unqualified circuits are really dangerous, and that is something that only a programmer can know if they've written incorrectly. Like if I'm using some clever workaround to get using my specific that only works on this specific field, that I can drop these constraints, that is something that the compiler cannot know, or well, we're not there yet at least. And so that is something that only the programmer can know, and there is a lot of responsibility on the programmer to get it right. Similarly, zero knowledge currently is at a state where to get high performance, you need to optimize a lot. We have seen this in our examples where if you write the program naively versus when you use witness expansion and other tricks, you will get orders of magnitude of performance increase. So that is again like an argument for the programmer is already assumed to be quite. There is already zero knowledge required from the programmer, so why not make it explicit? And some of the difficulties of this kind of larger type system can also be hidden away quite easily from the programmer by using polymorphism and inference. So in this case, we have polymorphism over the field, the stage, and the domain. So this function sums a list, and the input on the left here in the brackets, you see that n is some natural. You have $s that is any domain, or just a generic domain, and @d is a generic, $s is a generic stage, and @d is a generic domain. So this takes in a list of integers that are uint of n, so that is like field elements of n, and of the generic stage and domain, and returns the sum, which is also in the generic stage and domain. So the advantage of this is that we can do interleaving, where we can interleave on and off circuit computation quite easily. This is something that is very desired for more complex programs. We've seen this, we've seen off-circuit computation things be also implemented in other languages like Noir, but I believe for them you can only define a function to be executed off-circuit, but we allow a bit more control in here. We also allow Rust FFI, meaning that if you have a Rust function, then we allow you to call that Rust function directly without any, we don't even do any transpiling or anything. It will directly call the Rust function. The only thing is that you have to conform to our types.
What is FFI?
Foreign function interface, so that you can call functions from other languages without issue. The cost of this is that we've had to build an effect system where, for example, when you're branching off, when you're doing conditional branching, like an if statement, based on a off-circuit value, and that will that creates a wire in one branch but not the other. That shouldn't be allowed, because that can reveal the value of the condition, like whether the shape of the circuit will then tell you what the value was. And so that is not allowed, and for that we have the effect system. So now I'll quickly show an example of what we've done with our language, because we in parallel built the language and also built the use cases to use it. So the motivation for this use case is that in Estonia there was a electrical vehicle subsidy, which had some terms in it where you had to drive at least 80,000 kilometers in Estonia within 4 years, and 80% of it had to be within Estonia. So it Couldn't be that you just get the subsidy and then drive around in Finland the entire time. The way that this was done in practice was using odometers, but this does not allow the user to see their input data for the verification. So for example, if they believe that they have complied with the conditions, but the system gives them an error or like a lower number than they imagined, then they have no recourse. In our case, we will have the full list of coordinates, and then they can argue their claim much better. So we built this demonstrator for the ARPA, and then this is the overall setup where we have this GPS tracker, so it receives coordinates to the car. The car logs the coordinates and signs them, and then the user will be able to download the coordinates from the car to their phone, and then on the phone itself run the zero-knowledge proof with the verifying server. In this case, it says Arlington because we did it for a specific event there, but the principle is the same. And one thing that is really cool here is that we got our runtime and integration with the mac and cheese protocol from Galois to work entirely within the phone. So they would download the coordinates and then execute everything on the phone using the phone as the prover. And this is the performance that we got. So assuming 1 hour a day driving, which is the US average as I looked it up, and 1 coordinate per 30 seconds, which is again standard for fleet tracking GPS. We got that for 1 month's worth of coordinates on the phone. It took about 127 seconds. And then with Pi 5, we got much better results because of hardware AES. Now, when we had this use case built out, we wrote it using mac and cheese backend in mind. So we used Mersenne 61 as the prime. We used some extra features like ARIA inequalities to speed up our inequality checks. And to do that, we also used the verifier challenges. So that's like an extra thing that the protocol is providing us, that they have the capability to give us verifier challenges. But this is not always the case. So for example, when Ligero asked us to provide the use case for them as well, they required a different field. So one that was fast Fourier transform friendly. And as far as I know, they did not have verifier side challenges. So to do this, it was actually quite simple. Because everything is polymorphic over the field elements, changing the field only required us to change one line and then recreate the Poseidon parameters. And then we'll double check that some constraints are okay, but it took very little time. With verifiers challenges, those are a bit more complicated, and that is a topic that we wanted to truly tackle on because we want to support many protocols. There is always going to be a mix of feature sets. So we wanted to truly support all of the backends, and to do that we had to add conditional compiling. So we added the type predicates for the features that we support. So currently we have field switching, verifiers challenges, function gates, and vectorization. And the usage of those requires a type predicate, and when you're compiling, you are compiling for a specific platform or protocol, and that performs the check of like, okay, this thing that you're trying to do, does your backend actually support it? And if not, you can branch on that condition and maybe run a different version of the same thing. So what we had was that we had our inequalities were all patched to execute at the end. And in that, we had already built it so that if the verifier does, or if the backend does support the verifier challenges, we run the inequality checks in one way and otherwise another way. So in truth, creating the output for the hero only took us about like a few hours of work, and then everything was okay. So that's like the simplicity of being able to swap the protocols if you have built out the hardware for it. The circuit, the backends that we currently support are the SIV-IR, like the textual interface. Now we've also added Circom. We also support the VLE-based like MCK, mac and cheese, and we've also added ZKB++ as well, like recently. We're adding to that list this year. What we're adding, we're not entirely sure yet. And the feature set, yes, is like varied right now. So all of these things under Galois mac and cheese, those have been the things we've been able to achieve with them. Other things we have as well is that we have built out our standard library as we build these use cases. We have quite a lot of parsing work. We have the bigint so that you can do ECDSA no matter what your actual field of the protocol is. All of those things we've built out over time. We do want to make it so that we don't have to reinvent the wheel as much. So for that, we have the FFI for Rust, and we're also adding Circom imports so that if you have something already built out in Circom, you will be able to just import those into ZK-Secrecy directly and call your Circom from ZK-Secrecy. We have other use case examples as well. So now that our project is finished, we are able to switch over to open source. You can see the link to the GitHub there, and yeah, we have those also work as code examples for people to see how the ZK-Secrecy actually works. And that is everything from me. Thank you. There's a gentleman there.
Okay. Wait. Just, we want everybody to hear you.
It's not that. What I'm saying is not important. That's what I was going to say. What's actually prevents you from doing something like people have built sort of ZK, ZK DSLs in Rust. What is actually the limit doing, like using, like just kind of encoding all of this in the Rust type system and then using other compiler layers that somehow is a bit more open that way?
I see. One thing is that like our backend integrations are also important, right? So also any sort of optimizations that we can perform, and yes. So for example, with function gates, we have an annotation where you can say that, well, this should be converted entirely to a sub-process in the circuit. And I think that is something which I'm not gonna, I don't know if I can claim that you cannot do it, but like it's a reason why we did it.
More questions? Yeah, I wanted to ask, so you had this nice example with the car taking GPS coordinates, right? So who signs like the coordinates?
The coordinates in that case, well, the cursor I think is again in the corner. I cannot move my slides. But we need to establish a source of truth. In this case, we assume that there is a non-tamperable device in the car that only logs coordinates. Or it doesn't have to be non-tamperable, at least tamper evident, so that, well, if there is some tampering, we can know. So
yes.
The
car signs them, right?
Yes.
In that device, and then it transfers to the mobile device.
Exactly.
It doesn't do the proving.
It does not do the proving.
Yeah, okay.
With the Pi-Fi, we did ask, like, okay, what if it did do the proving? Because that is a device we used for logging. And but just in general, we wanted to put as few assumptions as possible into the setup. We felt that well, you need to get the trusted coordinates somehow, and that seemed the direction.
Yeah.
There's a question from the gentleman behind you.
Yeah, thank you for your presentation. I'm just wondering what the performance of your approach. So if we are comparing the circuit size from the manually optimized circuit, for instance, like if we are comparing the circuit from your tool and like ArcWorks library, so what's the performance of the circuit size? And also, is there any way to embed or include the outside optimized circuit in your specification?
I do not have these kinds of comparative performance metrics. To your other question, yes, we are adding the circum imports, if that answers your question. But yes, we do want to make it so that the users are able to import circuits that are already pre-optimized. We do currently include Bristol fashion circuits as well from the MPC realm. So those are already integrated. Where if you have, that is actually what we use for SHA-256 as well. We didn't want to implement that ourselves. So yes, for those really optimized circuits, you can directly import.
Okay, let's thank Raoul again.
Thank you.
Hello everyone, I'm Z. I'm currently a PhD student at EPFL working with Alessandro Chiazza. Today I'm going to talk about our recent work on security for proof carrying data from straight line extraction. And this is joint work with Ale, Shaha, and Elon. So before I get started on all the technical stuff, I want to give a very brief roadmap on what I'm going to talk about today. So the first thing I'm going to do is to introduce proof carrying data. And the short answer of what is proof carrying data is that it's just recursive composition of snarks. And it's very useful for efficiently verifying distributed computations. But in practice, there is a little issue, namely that PCD is actually deployed under the assumption that no matter how many recursions you do, the resulting PCT is as secure as the underlying snark. But all prior security analysis, they cannot show that. They actually show that there is a huge gap between the security of PCD and the security of one underlying snark. So in this paper, what we do is that we propose a new idealized PCD that model closely the hash-based PCD in practice. And we actually show that for this particular idealized PCD, it is as secure as the underlying snarks, regardless of the recursion depth. So this provides the first justification of the common practice that people use in deployment. So let me start with defining proof carrying data, PCD. As I mentioned before, PCD is very useful to enable mutually distrustful parties to perform efficiently verifiable distributed computations. So let's look at a very simple example. So now let's say that I want to sum 6 numbers, and I have 6 numbers and I have 6 distributed parties. They're pandas, not very smart. Their job, each of them, is to sum one number and give me a proof that their computation is correct. And then what I do is just I aggregate their results and also their proof together to reach a final result. So PCD provides kind of an abstract way to model this type of distributed computations in the form of a transcript. And here I just give an example of a PCD transcript with size 8 and depth 3. And what is this transcript doing? This transcript is saying that for each node, which represents one step of the computation in a way, we say that the node is correct if for the given compliance predicate phi, given the current data Z, current witness for the computation W, and incoming data and proof, the compliance predicate accept. So if that's true, we say that this node of computation is correct. And we say that, so what is the purpose of this proof here? In the previous example, it does nothing. It's just summing one number, 2 number. It's a P computation. It's easy to verify. But in general, for hardware computations, you actually need proofs. And this proof pi, it not only attests that the current node, the blue one, is correct, but also it says that every child vertex, every child computation here also has a valid proof. So this is a proof of proof. And then the corresponding PCD prover and verifier has the interface where the prover gets all the necessary information for the current step of the computation, the data and the witness and the previous node, provide a proof for the current node, which is proof of correctness and proof of proof. And then the verifier decides whether to accept or reject. And as any other cryptographic primitives, we have security guarantee for PCD. And in particular, what we care most about is this notion called knowledge soundness. And it's saying that for every bounded adversary, P, there exists an efficient extractor, such that this event happened with very small probability bounded by kappa. Namely, the prover outputs a predicate, outputs result, output proof, sent to the verifier, and verifier accepts. And in this case, the probability that the extractor cannot extract a valid transcript that is compliant with the predicate provided by the prover, this event is extremely small, bounded by kappa. So that's the security guarantee we care most about for PCD, and that's PCD. And as hinted at the very beginning of the talk, PCD is actually just can be constructed from snarks. And specifically, we can focus on snark for one particular relation, circuit set, which is saying that it contains the set of tuples of a circuit and assignment where the circuit accepts the assignment. So that's the relation that we care about for snark. And then snark prover and verifier just work as usual. The prover gets both the instance C and the witness A. The verifier gets only the instance. The prover gives a very short proof, and then verifier decide whether to accept or not. And similar to PCD, we also care about non-soundness for snark, which is saying something very similar. It's saying that for every bounded adversary, there exists an efficient extractor, such that if the prover convinces the verifier, then the probability that extractor cannot extract a valid assignment is extremely small, which is bounded by kappa arg, the knowledge-soundness error of the argument, or the snark. Okay, so we mentioned that PCD can be constructed from snark. How do I do that? The very naive construction that actually work to some extent is just to concatenate snark proofs. Now we go back to this very early picture we saw, a PCD transcript. Now we want to use snark to allow the prover to slowly construct up the PCD transcript. So how does it do it? The PCD prover is gonna run the snark prover for the predicate phi. And in particular, it view the predicate phi as a circuit. So the snark works for circuit set, which can testify whether the predicate is satisfiable or not. And then the PCD prover gives all the necessary information to the snark prover, and snark prover output a pi. And then at the end, the PCD prover just concatenates all the proof strings, that the input proof strings, pi1, pi2 it receives, and also the new proof string it received from the argument prover, and concatenate them together. The advantage of this construction is that this is what we hope to be true. The PCD, resulting PCD is actually as secure as the underlying snark. But the disadvantage is that this proof string grows linearly with the number of nodes you have in the transcript. So this is absolutely not succinct. You cannot achieve efficient verification. So the working proposal that people actually use is called the recursive composition of snark proofs. And in particular, the PCD prover and verifier just invoke the snark prover and verifier for circuit set for a particular recursive circuit C that I'm gonna define now. So the recursive circuit C, again, receive input, the current computation, and all the child computations. And it check two things. First thing, it check whether the current computation is correct by running it through the predicate that we wanted to satisfy. And it also check if there exist valid proofs for previous computations. So it runs it through the argument verifier, which kind of guarantees you that you have valid proofs for previous nodes. And then the circuit just returns yes, accept, if both check pass. And if the circuit returns yes, you are kind of guaranteed that both the current node and the child computations are correct. And then the PCD prover and verifier, it just run the snark prover and verifier for this particular recursive circuit. And the prover gives the proof, the verifier decides whether to accept or reject. So this is recursive composition, and unfortunately, prior works cannot get very good security for this construction, and in particular, the best analysis at the moment shows that the PCD knowledge-soundness error is upper bounded by something exponential in the depths of the recursion, which means that you don't have any security guarantee when the depth of the recursion is bigger than constant. So it actually still remains a very interesting open problem to find a battery analysis for this case. But today, we're going to focus on a slightly different PCD, a PCD that has a stronger notion of extraction that I'm going to explain in a minute. So what we show is that we actually prove a significantly improved bunch for PCD with straight line extraction, this stronger notion of extraction, or this stronger notion of notch-soundness. And we say that if we start with a snark with straight line extraction, then we end up with a PCD whose notch-soundness arrow is upper bounded by the notch-soundness arrow. So this is exactly what we want. This shows a significant improvement. In general, this kappa in our construction does not grow with the depth of the recursion, nor with the size of the recursion. But the bad news is that in practice, snarks actually have non-black box notch-soundness, and straight line extraction that I'm going to define in a minute only exists in idolized models. So how do we apply this theorem in practice? Why do we have this result? Why does it matter? So the main application of our result is actually we propose a new idolization for hash-based PCD deployed in practice is a PCD or quote PCD in the random oracle model. And then we can apply our theorem because this particular idolization is achieved by snarks with straight line extraction. And this provides the first justification for the popular practice that people use for hash-based snarks, hash-based PCD, sorry. And we also have more theoretical application. In particular, a few years ago, people already started to look at snarks with straight line extraction in other oracle models. And in particular, CT10 looks at the signed random oracle model, which combine a random oracle model with a signature scheme. And in their paper, they show that the notch-soundness arrow of the PCD in SROM grows linearly with the size n of the PCD computation. But if they use our analysis, they're able to remove this n dependency, multiplicative dependency on the arrow bunch. And similar thing holds for the snarks in arithmetized random oracle model, which came up 2 years ago. Okay, now the last missing piece is to define straight line extraction. What is this stronger notion of notch-soundness that we use in this paper? So let's start with something simpler. Let's first look at snarks with straight line extraction, which is the thing that we use to build our PCD by recursive composition. And there are usually snarks in oracle models. For example, in the random oracle model, our favorite idolized model, we still have a prover and a verifier. And again, let's focus on circuit set. So prover takes in the circuit and the witness. Verifier takes in the circuit. But both of them have also oracle access to the oracle function, the random oracle function f. So it's like an oracle gauge that they have. And then, as before, the prover just use this input and its oracle access to the oracle and provide a very short proof to the verifier, and then the verifier decide whether to accept or reject. And we say that the snark has straight line notch-soundness if there exists a deterministic structure E, such that for all bounded adversary, this event is, the probability that this event happening is very small. So the prover convinces the verifier, and then the prover sent the circuit, the instance, the proof, and a transcript, a trace, a query answer trace, which contains all the queries the prover made to the random oracle function f to the extractor. And then the extractor, the extractor's goal is to extract a valid witness. And straight line notch-soundness is saying that the probability that the extractor cannot extract in the event that the verifier accepts is very, very small, bounded by kappa arg. And we say that this is straight line because this extractor contrary to the previous one we saw, it does not depend on the prover. It only depends on the correct answer trace. And the wonderful thing is that in oracle models, especially in the random oracle model, this is achievable by our favorite snark, the Mikali snark, the one that is based on PCP or IOPs. So let's see with this snark whether we can use the previous recursive composition to construct PCD. The spoiler is that we actually can, but there's some modification that we need to do. So this is the previous recursion, the recursive circuit, and this is how the PCD prover and verifier functions. But there is an issue. The circuit C now, because of the verifier, the snark verifier now has oracle access to the random oracle. So this red F here. So now the circuit C become an oracle circuit. So let's recall that previously the C-set relation we are considering has circuit C, and if it just evaluates C of A. But this doesn't allow oracle access to F. So we have to consider a slightly modified relation where the circuit C is allowed to have oracle access to F, the random oracle. These two relations are actually different because the first one doesn't depend on the oracle, but the second one depends on the random oracle function that you have. And therefore, the snark prover and verifier we use have to be able to support C-set relation that depends on the oracle. And the way to solve this issue is to use a notion called relativized snarks, which was briefly mentioned yesterday night. So what is relativized snarks in an oracle model? Again, we use a very concrete relation, C-set with oracle gauge, where the circuit is allowed to have oracle access to F, the one we saw in the previous slide. And then we just do recursive proof composition. Now everything works. There is no violation in the interface or whatsoever. And then with this recursive proof composition, we're able to achieve PCD also with straight line extraction, which is saying that, again, there exists a universal extractor such that for all adversary bondage, if the adversary makes the verifier accept, then the extractor, given, again, the correct answer trace of the malicious prover, it's with very high probability, it's able to extract a transcript that is compliant with the predicate. So for the last few minutes, I want to briefly mention our main application, how to use our results to set security parameter for hash-based PCD in practice. So a brief warm-up is something I think a lot of you are already familiar with, how to analyze and set parameter for hash-based snarks in practice. So there is a very well-established three-step recipe, where the first step is you first give an idealization of the hash function that you use in the snark, because it's hash-based, which is a random function, and in particular, for any hash-based snark, where we can idealize it as a snark in the random oracle model if you use the random oracle to idealize the hash function. And the second step is to establish a concrete security bound for the snark in the random oracle model, which you can do, and there are analyses out there. And then the last step is to go back to the hash-based snark and set parameter according to the concrete security for the random oracle snark. So we have to be careful at the first step here in the idealization. This only works if the snark only have black box usage of the hash function. But we're very lucky because almost all snarks that we care about, especially the one based on probabilistic proofs, they satisfy this constraint. So let's see if we can just use the previous well-established recipe to model hash-based PCD. And in particular, we know that in the standard model, a hash-based PCD is obtained by recursive proof composition from hash-based snark. So what if we just idealize the snark, as always, because we like the snarks we have. In practice, they have straight line. They don't have non-black box usage of the hash function. But this is problematic because, as I mentioned very early, the security analysis, the existing security analysis is actually very expensive in the sense that it grows, the error bound for the PCD grows exponentially with the depth of the computation. So we cannot use this. But in general, practitioners still use hash-based snark in practice as if it's as secure as its underlying snarks without justification. Then the natural question to ask is whether we can use our results. In particular, we have relativized snark here, we have PCD here. Can we do a mapping like that? Can we do idealization like that? So the second attempt is actually to follow the arrow, the blue arrow in the previous slide. So what we want to do is that take a hash-based PCD, idealize it to a PCD in a random oracle model, and then do recursive composition from relativized snarks from in the random oracle model. And then apply our theorem, which shows that the arrow doesn't grow. But the first issue is that this idealization actually doesn't work because most PCD, hash-based PCD, have non-black box use of the hash function because of the recursion. And also, what's more troublesome that we don't know how to get around with is that there are impossibility results that I'm actually going to talk about in 3 hours. Recently we showed that relativized snarks actually do not exist in the random oracle model, and this is a very strong impossibility result. It's almost tight with the current non-existing constructions. And also there are very strong evidence showing that, and it's a popular belief that PCD actually do not exist in the random oracle model. And there are partial results proven by the very early paper, the Valiant paper, and Eurocre paper 2 years ago, and also my 2 recent impossibility results. So we cannot apply our theorem directly. So what can we do in this case? We have 2 issues, right? First, hash-based PCD uses hash function in a non-black box way. Second, this impossibility result in the relativized world. But one observation we can make is PCD, by recursive proof composition, actually only looks at the hash function to check correctness. It doesn't destroy the hash function in any way. And moreover, this relativization shows up only because the circuit C, the recursive circuit, is an oracle circuit. It needs to query the random oracle, but it needs to query the random oracle precisely because the snark verifier needs to query the random oracle. So that's the only reason why C is an oracle circuit. So the solution we propose is actually we can forward all the oracle queries that will be queried by C to the prover by asking the prover to attach all the queries C is going to make to the proof string. So then in the recursion, the circuit doesn't have to make oracle queries itself anymore. It only needs to check at the end of the recursion that all the forwarding queries by the provers are correct. So, but the caveat here is that forwarding the queries makes the prover non-succinct, but as an idealization, this is not, especially for security, this is not really an issue. So then we can apply our theorem. Take an hash-based PCD, idealize it to a non-succinct PCD in the random oracle model with straight-line extraction, which we can obtain from non-succinct relativized argument in the realm with straight-line extraction. This actually gets around with the impossibility results that I'm going to talk about in 3 hours because of the non-succinctness. And then now we're happy, we can apply our theorem, and this provides the justification for the popular deployment in practice on hash-based snarks. And that's all. Thank you.
Any questions?
we've heard a lot about like Fiat-Shamir, idealized model, and all these kind of things yesterday. Are you like scared that this particular setting might give us problems in that regards?
Not in particular. Thank you for the question. It's a great question, but not in particular because the whole like all the results we have in this paper and also even in standard model, the PCD security can be guaranteed once you have security for the underlying snark. And in particular, if you are able to, so in other words, if you are able to give me a secure snark whose security is guaranteed by whatever variant of Fiat-Shamir that you can come up with, then the PCD is guaranteed to be secure.
Yeah. Okay, let's thank Z again.